What's up, everybody? Welcome to another episode of CCT. So today we're going to be going over the valid triangles problem. Now, what this problem is asking is given an array of numbers, like, let's say 1, 2, 3, 8, 9, 10, something like that. It's asking for how many pairs of 3 are valid triangles. So what does it mean to be a valid triangle? I guess that's the first observation to make. It means in a triangle, every two sides must add up to be greater than the third side. So that means A plus B is greater than C. A plus C is greater than B. B plus C is greater than A, and that... Am I missing any? Nope. Okay, yeah. So all those 3 conditions need to be true. I probably shouldn't have sorted this because I didn't I didn't specify it was sorted. Let's give it 20 or something. So for example, in here, a valid triangle would be like 8, 9, 10. An example of something that's not valid would be, let's say, 1, 2, and 20. And that's because 1 plus 2 is not greater than 20. Okay? So, like in most interview problems, probably the best thing to start off with is your brute force algorithm. Okay, so how do you figure out, let's just figure out how you would do this with a brute force. So what I'm thinking is you'd have 3 for loops, so basically for I 0 to n, then for j, what would j go to? It would go from i's point to n, right? Because we could have like 3 pointers, but I mean the second pointer shouldn't be where the first pointer is. It should be the one directly after, or at least it should start off there. And for, let's get that k in, j to n, and what are we going to do? We are going to verify that it's a triangle. Perfect. Okay, we could just say verify, which will calculate, this is an O of n operation, calculate I, j, k. Okay, what kind of time complexity are we looking at with something like this? So, let's see, we have 3 loops, each looping through n roughly, so, and then this operation is an O of 1 operation, so we're going to have a time complexity of O of n cubed. Okay, so the first question is, how can we optimize this? I find when searching for stuff in an array, kind of like, well, let's see. I guess my thought process was, so if this array was sorted, so let's basically move this 20 over here. If it was sorted, what we could kind of do is we can prune a lot of this time complexity. So let's start the third pointer on the right, and let's keep moving it down until it is until 1 plus 2 is less, until 1 plus 2 is greater than it. So I guess in this case it doesn't help too much. Let's like make this, I don't know. Let's make that a 3. Okay, so we start here and we keep going here until 1 plus 3 is less than it. Sorry, until 1 plus 3 is greater than it. So I guess it's not going to be at all. Yeah, this isn't the best set of numbers. But basically, if you got to a point, let's say it's here, where these two numbers are greater than this number, and this whole thing is sorted, guess what that means? The rest of these triangles here, all of these are also going to be valid. I guess that one of the key observations is we know that this number plus this number is definitely greater than here. And we know that this and this is greater than this because it's sorted. If that doesn't make sense, take a minute to think about it. What we don't know is that this number and this number is greater than this number. And that's why we start from the right side here and we keep going until we get to that point where these two numbers are greater than this number. And then what we do is we have the index here. And what we could do is subtract it from the index here. So like, let's say this is index like 20 and this is index 1. That means we have 19 triangles. Okay, and then what we do is we move on to our next iteration, which is going to be, which is going to be pointing here, here, and then again we start the right pointer off here. Again, the same thing is true where we know that the first number and the last number are definitely greater than the middle number. We know the middle number and the last number are definitely greater than the first number. Again, it's the first number. It has to be smaller than both of them. So the sum of them is definitely bigger than the first one. And then we do the same process where we go this way. Okay, so what is our time complexity if we did that? Let me actually write that out a bit. So basically, instead of our last loop, we're going to do, whoa, what just happened? Interesting. So instead of our last loop, we're going to have for k is going to go from n all the way to j. And then we could verify, or sorry. If verify I, j, k, oh yeah, we also should be keeping a count. So if that's true, then what we're going to do is count plus equals k minus j. Now, forgive me for an off by 1 error here. Yeah, I mean, let me just verify this. So let's say, again, we're at index 20 here, and that this index is maybe index 2. That means we have this one, all the way up to that. Yeah, I do think it's just simply k minus j. There's no, like, k minus j plus 1 or something. Yeah. Okay, so effectively what we've done is we have pruned this iteration. However, pruning doesn't really cut the time. I mean, it cuts the time complexity, but not enough to change the polynomial and the polynomial of big O. So we're still at big O of n cubed. And what I mean by that is we're more like at O of n squared. Let me write that in pink. O of n squared and then times maybe n divided by a lot, probably. Because there is going to be a lot of pruning. But then you have to think of the worst case. Maybe there's not. Maybe like every case fails and it just has to go all the way to the end. So you got to consider that, and we're still at O of n cubed. All right. So the next thing I kind of thought of from here was that, okay, how could we optimize this? We know that this part here, we know the whole thing is sorted, but I'm thinking of optimizing the final loop, and what we're basically trying to do in this final loop here is figure out the place at which the first two, so this one and this one, are greater than, or the sum of those two is greater than the index on the right. Let me actually draw this in pink. So those two are greater than the index on the right. And we want to find that point. And we know that this part is sorted. Actually, the whole thing's sorted. And so what we were doing before is kind of a linear search, trying to find that point at which these two were bigger than the third index. But how else could we do this if it's sorted? Well, something that we could do is we could do a binary search here. Yes, it is definitely a pain because instead of an extra for loop, we have to do an entire binary search, but we could definitely do it. Okay, so what I'm going to do, so binary search as in you have a start here and an end here, and you're looking for when the mid or your target is a number greater than the first two, or sorry, is a number less than the sum of the first two. Okay, and then like if this was the answer, for example, here, these two would sum to be greater than that number, and those two would sum to be less than the number to the right of it. I'm kind of just telling you the condition of this binary search. So let's try binary search here for number less than sum of val I and j, so the actual value there, and index to right is greater than that sum. Okay, great. So what's our time complexity here? We still have the O of n squared for sure, but what else do we have? Well, we have log n now, right? Because binary search can be solved in log n, and that's an improvement. That is not only that's not just a pruning thing like the thing we did before. This is an actual always going to decrease the time complexity by some and change the actual polynomial. Okay? So you might think you're done here, but to get the O of n squared solution, which is the fastest solution, you have to think outside the box. So some problems to relate this to is kind of the 2 sum to target and 3 sum to target, where 2 sum you're trying to find 2 numbers in a list that sum to the number, and the 3 sum is when you find 3 numbers in a list that sum to a target. The 3 sum sounds very similar to valid triangles. And one of the optimizations there is to use this idea of 2 pointers. So let's draw that idea out here. So we sort the list. We have a first pointer. I'm actually going to start it here at the top. So that's going to be the largest number. And then we have 2 pointers here and here. And the blue pointers need to sum to be greater than the pink number. Right? And if that's true, then like we add 1 to our count or whatever. Okay? But here's the cool thing. Let's say the blue numbers are currently greater than the pink number. Okay? That means we have some slack. So we're going to count this as being 1. Then we're going to move it over here. We're going to count this as being 1 valid triangle. Let me use tallies for count. So that's 1 tally. Okay, it's going to move here. And let's say now the 2 blue pointers are, again, still greater than pink. So you could put another tally down. Again, since they're greater than the pink, we're able to move the bigger pointer, which is the blue, down so that the sum is guaranteed to decrease. Okay? So again, we move it over and it's greater than, we move it over, let's say it's greater than again. And now we move it over and it's less than the pink. So the 2 blues, so here and here, are now summing to be less than the pink. Okay? So we don't tally this. So then we move the left blue, which is the smaller one, over. And now we ask, are the 2 blues greater than the pink? And it's not. So we have to increase it, the sum. And to increase the sum, since it's sorted, we want to move up the left bound. Okay, so it's not greater than, for example, and let's say here it's greater than. Tally. Okay, since it was greater than, we can go down 1 here. And let's say it's greater than again. Greater than again. The sum of the 2 blues is greater than again. And we ultimately keep going and keep counting. And by having this 2-pointer approach where if they're greater than, we move this down, and if it's less than, we move our left pointer to the right. By doing this, we are effectively finding all of the valid triangles with this as one side in O of n time. This part is O of n time. That's something that we had to do in either n squared time before or n log n with our binary search optimization, but we could never do it. Now we could do it in O of n with this idea of 2 pointers on either side. And again, this only works because it's sorted, right? We had an n log n kind of overhead. All right, so then after we found all the valid triangles with this pink one, we move that over here, and we do this again. Okay, let me draw out some of this code here. So let's do for I is going to go from n to 0. Now we have a 2-sum thing. So while j is less than, actually, let me say j equals 0, k equals I minus 1. While j is less than k, we are going to see if j plus k is greater than I, that means we have room to move the right pointer down. So we're going to do count plus plus because they are greater than it. And then we're going to do k minus minus. Else, so it's smaller than, so it's not a valid triangle. We're going to move j up. Okay, so could I change the color of this? Sorry, I should have made this blue. Blue? Dang it. Wait, one more thing. Copy, delete, bring to front. Yeah. Okay. So this part here is O of n. And this part here is n. So by using this two-pointer idea, we have effectively turned our complexity all the way down to O of n squared. You will find this idea also in the threesome problem. So if you haven't done that, I encourage you to do it. It's very similar. It's just that you have to find three numbers, or you have to count how many combinations of the three numbers sum to the given target. Very similar to this, where we have three sides that don't have to sum to a target, but they have to follow these conditions. So valid triangles is harder than threesome, so hopefully you can do that one. Alright, so that's all I got for this video. Yeah, so I hope you enjoyed it, and I will see you guys next time.